So welcome everybody to today's session of Newton 1665 seminars. Today we have the pleasure to have Arthur Hebecker from Heidelberg University talking about Euclidean wormholes and their consequences for particle physics and cosmology. And before we start, I'd like to remind you that in order to ask questions, you can just either raise your hand virtually or just unmute yourself and speak up. And during question, you can also use the technology offered by Zoom. For instance, you can write on slides, on annotate and stuff like that. So Arthur, please, stage is yours.
Okay, so can you hear me? Am I visible and the slides are okay?
Yeah, everything's fine.
Good, very good. So then I'm very happy, I'm honored to be here and to talk to you about, well, basically the subject is a few years old review, and the topic was given to me by Alessandro when he invited me. So, but I decided that it's impossible to give really a talk about a 70-page review. So I will, roughly speaking, I will motivate why at the time we started to be interested in this very old, in fact, subject of Euclidean wormholes. And this comes with the gravity conjecture, so I will discuss that. And I will then discuss how wormholes may be applicable to real-world physics. And then I will come to more recent developments. I mean, I will first review the old problems, which are still unsolved, which are very severe, and then discuss some recent developments with some bias towards my own work. Okay, so the first topic, line 1, motivation with gravity conjecture. Second topic is why the wormholes appear there. The third topic is the old problems, and the fourth topic is some recent issues. All right. Yes, I will be happy to be interrupted. So if anybody wants just to unmute and ask a question, I will be very happy. I don't have to necessarily finish my slides. All right. So one key question that led to the whole concept of swampland is whether anything goes in the landscape of consistent four-dimensional effective field theories, or if you're a stringer, in string compactifications. So can we write down anything and UV complete it into gravity? And the question concretely is, are there general criteria for a given model not to be in the landscape? So not to be UV completable. And of course, more complicated question is whether such criteria can be formulated generically in quantum gravity rather than in string theory. And the picture that people always draw is this picture down here. So in red, dashed line is crazy stuff that anybody can write down. And if you think more carefully, sometimes it will be anomalies, sometimes you will have to include extra operators. And then you come down to the blue curve. And this is stuff that is completely consistent within low energy effective field theory. So you cannot detect any problem, but the claim is that only a subset of these theories is actually consistent in the landscape. In other words, has a UV completion in quantum gravity. So for this talk, two particular such swampland criteria will be important. One is no exact global symmetries. I will not comment on this. This is familiar since many decades. And the second is the weak gravity conjecture, which is by now also rather familiar. Let me still remind you. So naively, it says gravity is always the weakest force. But more concretely, it says that for any U1 gauge theory, there exists a charged particle with mass smaller than its charge in Planck units. So this is m Planck equals 1. And when I say smaller than its charge, I mean the charge being the product of gauge coupling and some possible integer number for higher charged particles. All right. So let's go on. What is the support for this? Historically, one important item of support is that in the absence of sufficiently light charged particles, external black holes are stable. And such remnants are believed to cause problems. One can understand very easily that indeed, if this condition Q over M is 1 is not satisfied, I mean, if the mass is higher, then black holes cannot decay, because actually this boundary here means extremal black holes. And you know that two extremal black holes can merge without force into an extremal black hole, which can then go back into two small extremal black holes. So this is the limit of when this process happens in a moduli space. That is the borderline case of the gravity conjecture. Now, however, this argument, even though it's very interesting and historically important, it's not clear how strong it is. I mean, why should there not be stable extremal black holes? So the argument that I like slightly more is the following. Quantum gravity forbids global symmetries. Let's take this as something we believe in. Then we should not be able to take the limit of small gauge couplings. Yeah, because the limit of a gauge theory with taking the coupling to 0 clearly will make it a global symmetry. Now the gravity conjecture can be said to quantify this on the basis of stringy examples. Namely, you can visualize a plot where I plot here the mass and here the charge of various particles in various string constructions. And it just turns out that in concrete string examples, you always get to populate only that part of the plot. You just never get to construct something here. And so given that you know already that you expect some constraint forbidding you to take the charge to 0, then probably this is the right constraint. Okay. So now it is not obvious how the gravity conjecture could impact phenomenology. There are various interesting proposals. I used the slide to list some of the people who work in this field, some good friends. And so a widely accepted application is to constraining large field inflation by constraining axions. And this connection to axions will lead us to wormholes in a few slides. So this is just a motivational slide here. And so in fact, I will not talk about the gravity conjecture in general, but about its application to axions. And for that, let me sacrifice one slide to remind everybody what an axion is. So for me, an axion is an axion-like field, to be more precise, because I'm not talking about QCD. It's just the following Lagrangian. So there's some scalar here, which is periodic. Down here, phi equals phi plus 2 pi f. And it couples like this to FF dual of some non-abelian gauge theory. Okay, so that's an axion. And this field phi clearly has a shift symmetry by a constant, because this is a total derivative term. But the shift symmetry is generically broken by instantons. Very well-known effect that if you have space-time, so here's time, here's space, then every now and then in the path integral, you will find a fluctuation, a local tunneling effect, in which f mu nu will be non-zero. And so these little bumps, tunneling processes with localized energy density, are called instantons. If you resum them, they induce a potential for the axion of this type, a cosine phi over f potential, illustrated here. Okay, so this is what I will mean by axion. Actually, let me step back, sorry. I should say that this little bump of energy, which is the instanton, which kind of is the object belonging to the axion, of course, in string theory, does not have to be a patch of FF dual energy or field energy. It could be some brain wrapped on some cycle. It could be some point-like fundamental object in string theory. So this is, of course, just the field theorist's simplest case. I mean, we'll come back to that. Now, to apply the gravity conjecture to axions, we first need to generalize it. And there's an obvious generalization, because if one writes down the Lagrangian in this way, we will see it generalizes to objects of other dimension. So first, let's recall what the Lagrangian is. Very, very basic. So F2 squared is just a gauge theory, abelian gauge theory now. Yeah, talking about gravity conjecture, abelian gauge theory, plus the action of the charged particle, in the sense that it's just the mass of a particle integrated over its world line, plus the coupling of the charged particle to the gauge field. There's a prefactor Q here, and then integral along the one-dimensional world line with the 1,4 potential. Now it's obvious how to generalize this. This generalizes to strings, domain walls, and so on by simply changing the number of indices or the form degree. So in any dimension, I have here some p+1 form field strength squared, and the integral here goes over the world volume of the string, domain wall, and so on. And the integral here goes over the same world volume, but the integral is of the appropriate gauge field potential, AP, p bigger than 1. Right, so now the interesting point comes when we generalize, or for us interesting point, we generalize to instantons. Namely, instead of raising the dimension, we lower the dimensions. One can also lower the dimension of the charged object. At which point, of course, if you lower the dimension of a world line, you get a point. So the charged object now is a point, and the action before is the integral here of the square of a one-form field strength. But that's just the kinetic term of a scalar. Then the coefficient here used to be the integral of some coefficient along the world line. It just becomes a number. A point, there's nothing with a number. And then eventually the integral of the gauge potential is just the evaluation of the scalar, which is a zero form, at the position of the instanton. So we are talking here about the theory of instantons as the charged particles of the Ugavi conjecture. And you see that by comparing this expression to this one. So here I write down again the instanton kinetic, the axion kinetic term, the non-abelian gauge field strength squared, and here's the coupling that we had before, 1 over f phi trace ff dual. So what happens is clear, right? The picture here where you have some gauge field and a particle propagating is replaced by having this picture where you have some zero form as a gauge field, and every now and then an instanton pops up. And so this is just by complete analogy. I can now take over, if I deeply believe in the Ugavi conjecture, the bounds. So Ugavi conjecture for axions instantons. Maybe it's a good point to pause. I mean, is that that's by now clear in the community, but since it's a broader seminar on Pheno, I decided to explain it. So are there questions? Has that been clear? Is anybody following the chat? No, I don't see anything. Okay, good, good. Let me just go on. So for instantons and axions, let us first worry about inflation, the famous application. The consequences are easy to derive. So we first recall that the instantons, I already explained, induce a potential. V of phi is e to the minus s instanton times cosine phi over f. Now, since for instantons, Q, the coupling, is, or the charge is 1 over f, you remember from the Lagrangian before, and what was the mass is now the action of the instantons, we have simply this replacement. So our old bound, m smaller than q, turns into the bound that the action of the instanton is smaller than 1 over f. Okay, so easy to remember, easy to understand. And now if we demand that s is always bigger.
Sorry.
Yes.
Artin, this is in Planck units.
Oh, yes. I apologize.
Okay.
Everything here is in Planck units. I would, yeah, of course. Also, okay. This mass smaller than charge, of course, only makes sense if you talk in Planck units. So this is basically the numerical charge times the gauge coupling times m Planck. And here also, S instanton is smaller than m Planck over f. So yeah. Good, so this is of course without Planck units. I mean, the action has to be larger than unity if you simply want to be in control, in the sense that the instantons form a dilute gas, so you can do any calculation. And so if S is required to be bigger than unity, then it simply implies that F has to be smaller than 1. And that means that large field natural inflation is in trouble. And this is a famous old application, which I will not discuss, at least not mainly. Moreover, even if F is smaller than 1, this is satisfied, one gets a lower bound on the strength of instanton effects. That is kind of the main point. So if f, this inequality turns into e to the minus s instanton is bigger than x to the minus 1 over f. So this coefficient tells you how strong the instanton effect is, and it is bounded below by the Ugavi conjecture. Good. So now comes
Can I ask something? So
yes.
Strong coupling is violated.
Right. So the coupling strength is a delicate thing. So normally, the Ugavi conjecture is used in the regime of weak coupling, right? It's a very interesting question, actually. And weak coupling in that context means f bigger than unity, right? So then basically, the Ugavi conjecture in this context of instantons tells you that the weak coupling regime, the regime where 1 over f is smaller, f is large, is ruled out. Or more precisely, this regime is not in the control, it's not a controlled regime. Your instanton gas is not dilute. Okay. So this is why how you supposedly kill large field inflation. But now I'm doing a different thing. Now I allow for f being smaller than unity. And at that moment, if you are very purist, you could say, stop. F smaller than unity is actually the strong coupling regime of the zero form gauge theory. So maybe you should not apply the Ugavi conjecture altogether and we are done. But a general proposal, made by now by many people and discussed by many people, is that no, we simply take the equations, we take this formula, and we trust it everywhere where it makes sense. And it does make sense in the regime of small f meaning strong coupling of the zero form gauge theory, but who cares? I mean, I apply this equation, I get a constraint on the action, and I know that instantons have to be a stronger effect than given by this exponential. Okay. So strictly speaking, I'm using the Ugavi conjecture in the strongly coupled regime of the zero form gauge theory. Does it answer your question? I see more confusion.
Yes. Okay.
I may have created more confusion. If I created more confusion, then just ignore it, just trust these equations, okay? Because it was only motivation so far. Namely, a distinct but Ugavi conjecture related to are gravitational instantons. And they will, as I will now argue, maybe produce the same story, produce the same effect without using this conjectured bound. So let me now remind you or introduce to you gravitational instantons. In fact, a particular type of them, getting Strominger wormholes. So the setting is extremely simple. There's Einstein gravity and one axionic scalar phi. And then the claim is that the following type of solution exists. Flat space, wormhole, flat space. You can discuss the second flat space as some extra universe, or you can close this cylinder to itself. Of course, these ends have to be distant so they don't interfere with each other. This solution simply exists in the Euclidean theory of gravity and the axion. And it's intuitively actually very easy to understand why it exists. So it exists basically because the axion changes as you go from here to here through this road. The axion changes. There's a gradient. The axion changes from one value to the same value plus 2 pi r, plus 2 pi f, basically. So it goes one period. And the gradient energy of the axion, roughly speaking, supports this road. And of course, the relevance for inflation will arise because these wormholes can be resummed and make the same effect happen that we previously had from instantons. So let me tell you how easy it actually is to derive this result. It's actually one-line calculation, a one-page calculation. So the underlying Lagrangian is Einstein gravity here, plus f squared d phi squared. And as I said, phi is a periodic scalar. Now I treat this periodic scalar as a zero form gauge theory. That allows me to dualize it. So it's a zero form gauge theory with a one form field strength. I use a Hodge star in 4 dimensions. I get a 3 form field strength, which is a field strength of a 2 form gauge theory. So it's a dual description with the coupling strength inverse and dB2 squared, or H3 squared if you wish. So now, at that moment, you see, I go back to the picture that's wrote here, which of course, if you cut it, has a cross-section of a three-sphere. We have 4 dimensions after all, right? So this three-sphere is supported by n units of H3 flux, of the flux of this gauge field strength. And the typical radius of this rod, let me call it R. And then the balancing of the two terms, I mean, gravity wants to make the sphere shrink, and the flux doesn't allow you to shrink. We have this relation. So this is the Einstein part, and Planck squared times the curvature scale, and it has to be the same as the gradient energy of the flux, which is n squared over f squared, just taken from here, and then the r to the minus 6 is put in using dimensional analysis. Yeah, 1 over f squared times r to the minus 6 gives you dimension 4, as it should be. So this equality of the two terms allows you, can be solved for the radius, and so you get here the radius of the stabilized wormhole. That's it. Up to factors of pi, which you can read in the paper of Giddings and Strominger, or of course in our review. This is the answer. So now I return to units where Planck equals 1 for simplicity, and I recall from all the stories that the action, I can work it out now, is 1 over f, or n over f if the instanton number is n. In other words, if there are n units of flux on the sphere. And very intriguingly, this coincides parametrically with the lowest action instantons of the Ugavi conjecture. So it's precisely what the Ugavi conjecture predicts you, just derived from a concrete theory rather than postulated. I will take it basically, so historically it was maybe the reason why I got interested, and many people got interested in this old story, but I think it's a motivation for me to take the Ugavi conjecture in this particular context seriously, and to think about, and also to take wormholes seriously. I mean, two different stories merge in a very interesting way. So now, the maximal Ugavi conjecture curvature scale in this wormholes road is square root f over n. You can derive it looking at the previous slide. I do not want to go to do simple algebra with you here. But this scale should, of course, not exceed the cutoff. So if your theory has a cutoff, you cannot look at space-time geometries which are more curved than a cutoff. So this f over n has to be smaller than lambda squared. Now, lambda is just the cutoff of your theory. And that fixes for you a lowest n where you can trust the calculation, and hence the minimal size of the instanton correction to the potential v of phi. Yeah, you see, you can kind of always trust very highly charged wormholes because they're always large. If you make, by contrast, if you make them small, you may run into trouble here. So now let me estimate the potential correction. So the correction to the potential, this cosine, this famous cosine, is e to the minus s. But e to the minus s is e to the minus n over f by the wormhole calculation. And that is at least as large as e to the minus 1 over lambda squared, where lambda is a cutoff. Or if you insist on proper units, e to the minus m Planck squared over lambda squared here. That's interesting, but it's actually not as strong as one would have hoped.
So, sorry, can I ask something?
Please.
Because I never really understood this point. So let me try to ask you. So in the case of gauge theory instantons, you have a coupling, okay, phi GG tilde, that actually breaks the symmetry. Okay? So I understand how you generate the potential. But
yes,
here, there is no coupling of the same kind. So how can you be sure that you generate a potential here? Is it a conjecture or is it a computation?
So it's a very good question. So there has at some point been some debate about this, in fact. So the historical way how to, which people, or the most simple-minded way, is to treat these wormholes here as half instantons, okay? And you simply sprinkle space-time with them and you sum over all of them. All right. And then people have pointed out, look, this is not consistent because actually they have to connect somewhere, and they may have to connect to the same space-time. And then if you sum there, it seems that shift symmetry is unbreakable because everything can shift, still be shifted in phi. Everything closes. And I think we argued against that point of view in our paper with Witkowski, Mangard, and Theisen. So you can read a detailed argument there, how you do the calculation consistently in the wormhole context such that you still see a potential. And basically then the story is that you need to have some initial state. And the initial state will include cuts through this wormhole, basically. And so I'm not going to repeat this argument here. And all of this then, so let me stay here. All of this then in the end, from my perspective today, is actually insufficient and unsatisfying, because what you really need to do is you need to include, fundamentally speaking, baby universes in your description. In initial state, fundamentally initial state baby universes. And I will come to that in 3 slides. So maybe you can wait until then, and then you will see what the meaning of this calculation really is from my present perspective. But there are various levels at which you can do that. At the moment, I'm at the naive level of treating these wormholes as a UV completion of the instantons. But I agree that this can be criticized. And what the outcome of the criticism is will be clear in 3 slides. Is it okay for the moment?
Great.
Arthur, I have a related question that probably you're going to answer in 3 slides, so just say so in case. So what does it select the special values of phi? Because if you bring in the shift symmetry, right, something has to select special values of phi. Is the initial state you're going to discuss soon, or is it something else? Like, why a potential with a minimum at a given phi rather than another one?
I would say that indeed the baby universe state selects the values of phi.
Okay, so that's okay.
It's my short answer. But as I said, the story is more complicated. You need to read our paper with Theisen and see how we criticize and debate the arguments by Heidenreich. And then you can decide whom to trust. But I think all of this is now. I wouldn't argue either of those 2 papers anymore. I would say the problem is alpha parameters. I will come to that.
Okay, thanks.
Good. So where was I? Okay, gravitational instantons. So gravitational instantons, not to prevent inflation. If I just trust this correction for the moment, the relative correction must be small. So meaning delta v over v must be small. So e to the -1 over lambda squared over h squared must be small. So for Planck scale cutoff, this is never possible. So really you rule out large field inflation. However, if the UV cutoff is taken small, which is possible because you need the UV cutoff only to be as high as your Hubble scale. You don't need it to be a Planck scale. So if you take h, and you take h much smaller than unity, and you take the cutoff to be h, then everything can be fine because this correction to inflation is e to the -1 over h squared by h squared. So at small h, I mean for relatively low scale inflation, just below the Planck scale, it actually becomes small very quickly. And so it's hard to make an argument against inflation in such a fundamentalist approach. All right. Sorry, let me. Oh, that is very bad. I apologize. So at this point, this discussion of actions and of wormholes and so on, I remember that I put in a reference to recent work, more recent work. Here should be more recent work. So more recent work about wormholes and their actions and Ugavi conjecture can be found in particular in a recent paper by, remember, I think Andriolo, Gary Hsu, Oguri. I'm sure I simply somehow uploaded the old slide, so I will put it on the slide here. So if you go there, you will see many more details. This is just the old story here, but I will not go there. So apologies to Gary and company. I will discuss something else now. Namely, I will come to the point that phenomenologically, even if I don't care about inflation anymore and I don't care about the fundamentalist question of the gravity conjecture, wormholes remain very interesting, both conceptually and phenomenologically, in the small f regime. Gravitational instantons, small f axiom. This, of course, goes back, I mean, in the old days, wormholes are an old story. I think Alonso and Urbano started the most recent debate of this. And then there's a very recent paper on Alve Escudero, which I looked slightly critical at. I mean, there's very strong results claimed. So you can ask me in the discussion. And I will just want to give you a few points why the small f region is interesting. So for example, consider a QCD axion with a relatively high f. By relatively high, I mean gut scale. So the wormhole effect may be relevant as follows. So there is a potential for the axion coming from QCD. Everyone knows this famous potential. This is from summing QCD instantons. But then the same axion is subject to wormhole corrections with in principle a different phase, as we just discussed, as in fact Daniela just asked me. And this term is suppressed by some power of a scale, of a wormhole scale, but e to the minus s wormhole half, if I interpret the wormhole as half instantons. And so once this term here becomes dangerously large, you lose the solution to the strong CP problem. So that happens for f bigger than 10 to the 16 GeV. And so it's very interesting that there is an observational consequence. In principle, you can discover a situation when you can discover a situation when observations contradict quantum gravity, if you wish. An interesting possible observational consequences arise also in the context of black hole superradiance by axions and ultralight dark matters. I will only comment on one of those, namely the fuzzy dark matter story, again started by Alonso Urbano, and then there's also some further comments in our work. So fuzzy dark matter is by definition so light that its de Broglie wavelengths affect subgalactic structure formation. So the mass of this type of axion must be smaller than 10 to the minus 21 electron volt. Well, since it's exponentially suppressed, it's conceivable. It's nothing unnatural about such a light axion. Now, if wormholes are the universal model-independent effect of shift symmetry breaking, then this fixes f. I mean, this mass is related to f by this relation. M squared is x minus 1 over f. And at the same time, the abundance of fuzzy dark matter, because it comes after all from misalignment, is given by this formula. So the abundance is related to some power of f and some different power of the mass. And together, you can easily see that these two relations actually clash. They clash by a little bit. So one finds that, that m should be slightly higher than 10 to the minus 19 EV if you want to satisfy the wormhole-induced potential expectations. So that's again very interesting. I mean, you can get around this bound. Of course, it's not something set in stone, but it's interesting. There's potential observations which could test some physics at such an incredibly high scale. Okay, so but now the rest of the talk I will actually talk about more abstract and maybe crazy stuff, because once you see this is interesting, and then you should start thinking more carefully about where this comes from, whether you believe the theory behind it. And that opens a whole set of new problems. So let us revisit some very old fundamental conceptual issues of Euclidean wormholes. Namely, so my claim first is once one allows for wormholes, one has to allow for baby universes. It's clear from this picture. You have some space-time and you allow in the path integral for contribution when such a wormhole connects 2 points. Okay? And these 2 points may be separated in time. So you can cut here and think of the following process. Your space has spit out a little baby universe, a 3-sphere, and later on this 3-sphere will be absorbed, like a pair creation annihilation process, quantum mechanically. Now, if you allow for such baby universes, then as part of your Hilbert space, then with baby universes comes a baby universe state, because clearly your initial state from which you start already may include some of such spheres. Spheres present in addition to our infinite or very large universe, 3-dimensional universe. So this is information coming from basically such a process. This is what your state is. Just our universe with 1 baby universe, our universe with 2, and so on and so forth. I'll come in a moment that this leads to alpha parameters. So now, crucially, the following happens. Let me take a different perspective. So alpha parameters, which encodes baby universe states, actually are introduced by getting rid of a disastrously looking bilocal interaction. Namely, let me think again about a path integral of quantum gravity where I include all these wormholes. And here phi is some field. For example, the axiom could be any other field which is present in the background where you glue in this cylinder. Now, clearly, if you exponentiate, if you sum over all such contributions, you get a term x integral phi of x1, phi of x2, integrated over all space. And you get it exponentiated because you sum over 1, 2, 3 such universes. This is unavoidable. And now a simple algebra tells you that you can rewrite this as an integral over alpha, alpha being just a number, of x minus 1/2 alpha squared plus alpha phi of x. You do this integral, you know, standard completion of the square, you get this term on the left. So, but this here, if you take alpha as constant, is a perfectly fine local interaction. So here you see that the wormhole, like an instanton, actually connects and just sources some operator involving the other fields. But then in the end, you have to integrate over the alphas. So this can be argued also without a path integral directly from a state. I will not do that. It's been done in Preskel and Coleman's papers in the 90s. So basically what we see is in the concrete single axion case, an alpha parameter now governs a naively calculable e to the minus s cosine phi over f term. And all you get from this expression is the order of magnitude that you expect, but you don't get the actual number. What is worse is that actually all coupling constants get renormalized in this way, not just the coupling of the axion. And hence, in a series with alpha parameters, in a series with wormholes, in principle, nothing is predictable because this Weber universe state can affect all operators, including the Einstein-Hilbert term, cosmological constant, etc., because any field in this background, of course, feels to some small extent the presence of such a vertex here. All right, so this leads to many, many conceptual issues. So most naively, if you measure something in 4 dimensions, we measure alpha, and so we collapse our state to a particular value of alpha. But this is maybe too naive, because in a global perspective, you need to integrate both our 4D geometries and alpha parameters at the same time. If you do that, like suggested in this picture, that you have a state involving both many universes and many wormholes, and you have to integrate over all of them together, including the sizes of these universes. Then something happens that is known as the Fischer-Susskind-Kaplinowski catastrophe. Namely, you get dominated by large wormholes, by strong effects of large wormholes. So you're driven in the path integral. I mean, basically the integral over the big universes overcomes the exponential suppression by the action of the wormhole. Another key problem is that integrating out these wormholes clashes with locality on the CFT side of ADS CFT. So I will not discuss this. This is reviewed at the end of the paper by Akani Hamed and collaborators on the wormholes, and it underlies a lot of discussion, recent discussion in the SYK context, where also wormholes play a role. And finally, just integrating over the alpha parameters is clearly not sufficient. I mean, one needs to consider the full quantum dynamics of them. And that is, in fact, another interesting subject. For this, let us look at the case of 1 + 1 dimensions. So let me do all I just done in 1 + 1 dimensions, in 1 + 1 dimensional space-time, with a number of scalar fields. Then, of course, this is something which we know as string theory. And the alpha parameters, in this case, characterize the geometry of the target space. Indeed, you all know the famous string theory picture, how a string worldsheet embeds in space, where space is parameterized by scalars, x0, x1, x3, which are fields in this theory. And of course, this string worldsheet, through loop corrections, allows you to include such wormholes. And you even can radiate strings which become part of the background. So the string interacts with this gravitational background in that way. And so really, the alpha parameters are the background fields of string theory, the Tandy fields, and their quantum dynamics is of course part of the theory. And this raises very many complicated issues, and it's completely unclear what the analog of this in 3 + 1 dimensions is. I mean, what would be the target space in which our four-dimensional world sheet is embedded. What is this quantum dynamics? So given this, in fact, one really changes perspective. At that point, one starts to desire to dismiss wormholes altogether because this leads nowhere. I mean, this is a horrible story that opens up. But this is not so easy because, I mean, how you dismiss something that's formally there in your path integral? We know that in string theory, wormholes correspond to string loops and are necessary part of the theory. And you cannot dismiss them. String theory would become inconsistent. And you cannot forbid topology change for the same reason. So maybe there's a good reason to forbid topology change just in D larger than 2 and not in 2 dimensions. So that's one way out, right? String theory is allowed to have these things. We are not. Moreover, arguments have been given against Euclidean wormholes, against specifically giving Schrödinger Euclidean wormholes using negative modes. Negative modes in the expansion around the classical solution. The existence of the classical solution is undoubted. The question is whether it has the required single negative mode for interpreting it as a tunneling process. If it has more, that may be a problem. So this is, however, contradicted by other, and some authors claim it, some others contradict it. There's debate going on. So while this is technically still an open issue, I do not think that this is a strong enough objection. Let me explain. So I should emphasize that there's recently work here, for example, by Hertog, Trigiante, and van Riet, but I will try to argue that even if this work is right, and the Giddings-Schrödinger wormhole is not a good solution, it's not a good tunneling process, we can't get rid of the problem. So namely, let's consider that we allow for a non-zero amplitude for our universe to transit to our universe plus a baby universe. Once we accept this, it's hard to forbid the reverse process, right? So as a result, we already have wormhole effects. And the negative mode issue may simply be saying the following. Giddings-Schrödinger simply is not a good approximation for the amplitude, but the amplitude is there at some level. So imagine I have a process radiating a baby universe and absorbing it again. I do not control this region because the negative mode's here. But it's still, having negative mode doesn't mean the process is not part of the Hamiltonian. You see? Just that I can't calculate it. Okay, so now final comments, some more recent developments. So there's a 2-slide comment related to stuff which I do not understand very well, maybe not at all. Namely, recently, I mean, all of you have heard about this, a proposal has been made about calculating the entropy of evaporating black holes using the so-called method of islands. And the concrete mechanism which is involved in this actually is related to Euclidean wormholes, which play a central role in the replica trick calculation of the entropy. So that has led to some renewed interest. Maybe if this story works out and is considered to be, established, then of course you cannot dismiss wormholes because they are an important part of something as fundamental as the black hole entropy. Motivated by this, a new 2D toy model developing Coleman's original baby universe calculation has been suggested very recently. So Marov and Maxfield's this year's paper. Basically, the generalization is that they allow for more complicated geometries here. Yeah, it allows you not just this type of single wormhole, but it allows you to sum in a toy model, as I said, only topological 2D toy model, allows you to sum over all such topologies. And in particular, part of their proposal is to mod out the naive baby universe Hilbert space by a certain equivalence relation. So roughly speaking, the transitions 1 baby universe to 2 baby universe and so on is used as a gauge redundancy. So the baby universe state becomes much smaller. In their case, it's still large. It's not one-dimensional. But it has been proposed by McNamara and Wather that in fact, if one can do the same calculation in 4 larger dimensions, one should find that the baby universe Hilbert space is in fact precisely one-dimensional. So that would mean that you cannot remove the effect of baby universes completely, but you get rid of the arbitrariness of the other parameters because there's just one state which you can consider. Now, this is all, I think, conjectures because we cannot at the moment really do proper calculation like that. in D larger or equal than 4. The motivation is a particular calculation done in 2 dimensions. So let me end. I think I still have a few minutes, right?
Yeah,
Let me end.
Don't worry.
Sorry?
Don't worry, yes.
Yes. But maybe I'm a bit fast here. Maybe there are questions concerning this whole story. I mean, this is I'm now slightly changing gears, so maybe it's a good point to somebody wants to ask a question about these recent developments. So I think the punchline is that, yeah.
Can I ask a question, please?
Yes. Who's speaking? I can't see you, but okay.
Yeah, I'm Shondipan Shengupta from India.
Okay.
Okay, so I was wondering, in Gidding-Strominger's original work, there was no mention as to what kind of topological invariants could be associated with this instanton configurations, right? Which is typically how it happens in gauge theory.
Right.
Okay, now later on it was shown that this Gidding-Strominger Euclidean wormholes can actually be associated with some topological invariant in gravity theory, which is called Nye-Yan invariant. It's a torsional invariant. My question is, these topological numbers are parity violating numbers, these Nye-Yan numbers, which actually are associated with these axionic instantons. So can you, essentially what you are doing is you are relating weak gravity conjecture to this Euclidean wormhole solutions. Now my question is, can this conjecture and the associated bounds be used to infer something about this theta parameters in gravity for the Nye-Yan invariant? Or in other words, parity violation in gravity through these instanton effects?
Oh, I apologize. I mean, it sounds very interesting. I have not thought about it in any detail at all. I mean, as the invariant that you mentioned is new to me. I would have thought, there's simply one side that's introduced very naively. Okay. And I cannot answer. I am sorry. I mean, interesting point. I cannot answer. Okay,
sure. In fact, I can send you the reference if you want later.
I'll be very grateful. If you send me the reference, I will be very grateful. Look at this. Yeah.
Okay, thank you.
Thank you. More questions? Good. So now let me, last 10 minutes, discuss some recent work.
One question, please.
Yes, please.
Yeah, it's me, Alex. This thing about is there new evidence about this claimed reduction of the baby universe Hilbert space by the modeling out to be one-dimensional? There's this claim by McNamara and Waffer's paper, but is there new? I mean, like, what's the status? How strong is the evidence for this?
What do you want me to say? I mean, I think it's very hard to have. Well, the evidence they provide, I think, is because once it is true, other nice things happen, but you can't do the calculation in D larger or equals than 4. I mean, they relate it in a nice way to no global symmetries and other expected things. But it's more I would say the evidence is it would be nice to have such a conjecture, not I can derive it. Okay.
Okay, yeah. Okay, so this hasn't changed. I know that was the status since we last discussed, but there was no change in that. I mean, you have.
I could be missing something. I apologize. This is not. I mean, this is. I thought if I give this talk about wormholes in general, I cannot not mention these recent developments, but I have not worked on them actively. Okay, so my apologies if I missed something important here. Maybe someone else can jump in and say something about.
Because I also don't know more than this. I was asking.
Arthur, it's John here.
Please,
hi, Arthur. Yeah. As you say in your slides, but I think it's important to emphasize to people that McNamara and Waffer claim that D equals 2, D equals 3, and D equals 4 or greater are very different from each other. And they explicitly claim that D equals 2 models have very different physics, completely different physics. It's no longer one-dimensional Hilbert space, right? Baby universe Hilbert space.
Yeah, they claim one-dimensional in D larger equals 4.
Yeah, yes,
but
yes.
Not, of course, not in 2 dimensions because you know.
Yes, exactly. So there's a real problem about finding supporting evidence for this because I don't think we have any exactly solved model.
I agree. I totally agree. Yeah, sure. But I cannot definitely say that nobody improved on that. And there have been a few papers the last few months citing that and using that. Okay, anyway, so let me
Thank you.
Yeah, thank you. Good. Let me make one last point related to the whole story and use the opportunity to advertise some, as I think, very interesting work which we did recently, in fact, with John Mark Russell and Tristan Dowse and Sasha Leonard. So axions are scalars with a discrete shift symmetry, which is gauged. Crucially, it is gauged. Okay, so you cannot break the discrete shift symmetry, the shift by 2 pi n. Wormholes and instantons break its continuous shift symmetry very weakly, non-perturbatively. That was the whole story, I mean, the main part of the talk. So a natural question now comes to mind, can this be used to apply the gravity or swampland logic to quantitatively constrain global symmetry violation? And by global symmetry violation, I don't mean the violation of the shift symmetry for the axion, which we already discussed, but of linearly realized global symmetries, like global symmetries which really protect particles from decaying. First, such attempt has in fact been made invoking the familiar black hole evaporation effect by Fichet and Saraswat. And their claim is not closely related, I think, to this gravity or wormhole logic, that in the thermal plasma, the black hole-induced violation effect of global symmetries should not exceed the effect of symmetry violating local operators. It's an interesting claim, but in the end, the above black hole argument is simply a new conjecture, which is interesting, but it's a new conjecture. By contrast, in our analysis, we claim that for an important subclass of gauge-derived global symmetries, one actually may be able to produce a derivation of a bound from the gravity conjecture. So let me sketch this derivation. This will be my last point. So what does it mean to have a gauge-derived global symmetry? It means something very standard. Namely, you gauge an axion with a U1 vector field. It's the same as spontaneously breaking a U1 gauge theory. And the leftover in the infrared are just the light U1 charged states, if there are any such states. And they are now protected by a global symmetry because the vector that gauges, that couples to them normally, is massive, it's heavy. So as a result, in this gauging process, instantons in fact automatically destroy globally charged particles. So as you can understand in a few lines, which I don't have time to discuss now, is if you combine two gauge theories like this, like a zero form with a one form theory or one form with a two form theory, then a certain topological relation between the charged objects of the series emerges unavoidably. And in this case, it is such that the world line of the charged particle simply ends on instantons. It's a necessary way in which these charged objects combine. And that means that whenever you have an instanton, the charged particle disappears. And so you get to violate your originally gauged, now global symmetry through an instanton. So by the gravity conjecture for axions, the particle number violation is suppressed. So e to the minus s instanton is e to the minus m Planck over f. You remember that? Moreover, according to the magnetic gravity conjecture for axions, such a theory with an axion has a UV cutoff, which is low due to light strings whenever f is small. So that's just an application of the gravity conjecture logic to this particular theory. Hence, in total, combining these two formulae, you get a global symmetry violation, which is bounded below by e to the minus s instanton, which is e to the minus m Planck squared over f squared, over lambda squared, just by plugging this f in here. And this is extremely intriguing, I think, because the bound parametrically is in fact the same that Fichet-Saraswat derived from their black hole logic. And this brings me back to the main subject of the talk, it is the same bound expected from wormholes. So because as wormhole is, of course, the derivation I already gave you before, m Planck squared times the Einstein-Hilbert term, and this is m Planck squared over lambda squared if the wormhole curvature is as high as your theory will allow. So you immediately get this factor as well. And so now you have kind of three different logics, of which I think probably the gravity conjecture is the arguably the strongest, telling you how the violation of global symmetries is unavoidably constrained from below. Well, unavoidably means in a particular subset of so-called gauge-derived global symmetries. Okay, so this brings me to the end. So let me summarize. So the gravitational conjecture for axions demands certain minimal action instantons and hence certain minimal potentials. That's the key statement. Then the question is, can we independently of this conjecture have an argument what the dynamics realizing this instantons is? And indeed, wormholes may be the universal semi-classical counterpart of the gravitational conjecture instantons. And these instantons, they do not constrain inflation strongly, but they may have other interesting applications at small f. But I think if one is honest, once you talk about them, once you allow for these wormholes, then they come at the price of alpha vacuum and alpha parameters. We discussed this ambiguity of the quantum gravity state of our world. And so maybe the main conclusion is that I think based on what I just said, we should keep struggling with these fundamental unresolved issues. These are very fundamental and very unresolved issues, which I think are important and interesting. And so maybe last point in the talk, I explained the recent result that the gravitational conjecture provides a universal bound of the same parametric size as the wormhole effect, e to the minus 1 over lambda squared, for the breaking of linearly realized global symmetries. All right, so I think that's it. Thank you very much for your attention. Please ask.
So thank you, Arthur. So we already had a few questions, but let's have more. So anybody could just speak up or raise hand or write in the chat. Otherwise, I have one question. It's actually related to the recent work you mentioned by Alvey and Scudero. And in that work, they stress the role of the radial mode. So if you have a radial mode, they essentially, it was based on an old calculation by Linde, Kallosh, and other people. They say basically the physics that happens is that this radial mode becomes Planckian, and in this way you don't have any more this separation of scale between f and m Planck, and so you don't have any more a suppression, so a large action, but the action becomes logarithmically big, and this changes a little bit the story, I would say, right?
No, I would interpret this paper very differently. So technically you said it correctly, but the result is, if true, is completely groundbreaking. Namely, it means that you get, once you have an axion or any field with a U1 direction, you get non-suppressed, non-exponentially suppressed violation of the corresponding symmetry. Now, I did not fully understand the analysis yet. I have a doubt because it's a classic result and also a result, I mean, we checked it also in our paper with Mangard, Witkowski and Tyson, which I at some point referenced. There's a story that you can calculate explicitly the expected string theoretic case. Namely, when the prefactor here, let me look for the place where I have an action. So this f can be dependent, or it can be a field here, right? And in particular, this f in string theory normally is a field. It's exponent of some dilaton type field. And the dilaton type field has a Lagrangian. And so it's a very standard story, and you can solve the wormhole explicitly, and you get a mild modification by an order 1 factor for all coefficients of the exponent. So if the field is parameterized as some, let me call it chi, this is e to the chi, e to the alpha d chi with some coefficient alpha and d chi squared, then I know the solution. And it changes the result by a factor of order alpha, and alpha cannot be large or small. Alpha is a particular order 1 number, and all the story, otherwise I wouldn't have discussed the story, seems to be completely consistent and not changed significantly by the presence of these dilatons, or by field dependence of f. Now, the model that they look at is slightly different. The model is this field f is combined with just the kinetic term df squared, so no exponent. So maybe this is a difference. And
this
also
is called the radial mode, let's say.
and also they have a potential m squared phi squared negative and then plus lambda phi to the fourth or f to the fourth. So I have not yet been able to pinpoint exactly where the difference arises, but it seems to be, I find at the moment still very hard to believe that basically, you know, the effect is so much stronger and all the exponential suppression story is wrong, simply speaking. And I mean, the best outcome would be that yes, their paper is technically correct, but no, you cannot go to large values of f using that Lagrangian that they use. String theory has a different Lagrangian, and the result there is always suppressed such that it, I mean, what I said here is roughly correct, and the exponential suppression is true, and so on. But I cannot be certain. I did not study enough to be certain. Okay.
Okay, thanks.
So, Arthur, may I have a comment?
Yes.
So, sure, I agree that maybe within a string theory, so if the action is part of a string theory multiplet, then that could happen. But that's precisely not what we consider, indeed. So,
but can you explain? Okay, good, very good. I didn't see that you were here before. Okay, very good.
Yeah.
So explain. So you know that, I mean, even without let me skip the potential. There's no potential, right? Mm-hmm. Having no potential makes things better for you. It's more easy to move the field F, right?
Yeah. So actually, the result is broadly independent on the potential.
How can you contradict the? I mean, you agree with the axion statement I just made. I mean, with the delta statement.
With the free axion coupled to gravity, I fully agree with the calculation.
No. Let me replace this number here by x to the f.
Yes, and if you add the dilaton there, yes, I agree. It's
fairly similar. In that case, nothing particular changes. You know, the result is maintained, yeah. Right? You agree. So how can so in your case, you make this change e to the f even slower. So it's even harder to kind of shift the field. But your suppression effect is weaker. It seems to go the wrong way around, because in string theory, if you shift the canonical field, the coupling here can change exponentially. That's a very strong effect. In your case, it's linear, and still you get a stronger effect than the I'm just puzzled. I mean, I would really like to have intuition about that. Can you see my point?
Yeah, it's... Okay, so it is true that in the dilaton case it's exponential, but at the end the dilaton doesn't change too much, right? Within the profile. Whereas what happens when you consider the scenario we consider, that is what Kalos and Linde considered 25 years ago, and also Abbott and Weiss, is that the dynamics are such that f takes, goes up to the Planck scale near the wormhole throat, and that reduces a lot the size of the wormhole, and therefore lowers the action.
Well, but you see, I hear you. I mean, you're just stating the fact, but I'm surprised because making this effect here. So if I add to this term a kinetic term plus df squared, I make f a field, I add df squared. Okay.
Mm-hmm.
And then then I have a solution which you say allows this f in the wormhole to become so large that you are, very little suppressed. Yes. By contrast, if I have e to the f here, that should make it more easy to make this coupling large. But I mean, the same shift in df will make this coupling grow faster if I have e to the f.
Right, but it will depend strongly upon what the f values are, right?
Yes, but I mean,
in the dilaton case, which typically is very smooth, whereas the change we find is exponential.
I mean, you see, okay, I'm confused. It seems to me that your model, so if you, for example, made it somehow much easier for this f to change than the string case, I would not be surprised that you are getting a result which suppresses the effect, which makes the effect stronger.
Mm.
But it seems to be goes the opposite direction. But maybe something's wrong with my intuition about which functions of f are allowed. Anyway, so we need to clarify. I mean, I think there is some intuitive explanation missing of why the linear case contradicts the dilaton case. Let's put it like that.
Okay, so more questions? I don't see any. In the chat, by the way, Sandpan just wrote the reference he was referring to. And I think there are no more questions, so we can close the session, and thank Arthur again for the nice seminar and the nice discussion, and see you next time.
Thank you very much for coming. Thank you. Thank you. If you want to chat, I mean, as long, I mean, I'm staying here. If more questions.